while any broken law of physics is no longer a law of physics that is pure logic. This is due to the fact that physics is the description of the cosmos. But something has broken our physical laws, and that is black holes. But those laws are still part of physics, isn't that strange? It is. After all, we're talking about black holes, which are unexplored realms. So it's definitely going to be strange, but the question is, what happens within a black hole that defies our understanding of physics? Hello and welcome to Z. In today's video, I'll take you to a black hole and explain what happens within that violates our physical rules. But before we go, please subscribe and click the bell button. In 1783, an English philosopher named John Michell had an epiphany that would lay the groundwork for one of the most cryptic and mysterious celestial bodies. Building on Newton's theory that light is composed of small particles, John Michell realized that if these particles emerged from the star's surface, the gravitational pull of the star would reduce their speed, similar to how projectiles behave when fired upward from Earth. Michell also proposed that by monitoring the decrease in the speed of light from a star, the mass of the star might be calculated. Moving on, Michell recognized that in order for a projectile to escape the gravitational pull of a star, it had to move faster than a specific speed known as the escape velocity. The escape velocity of a star varies with its size and mass. What if there are stars with such a tremendous gravitational pull that their escape velocity exceeds the speed of light? He discovered that light from such stars could not escape them and would instead fall back to their surfaces. As a result, he proposed that such celestial bodies would be invisible in the cosmos since no light would emanate from them. This was the first time a notion pointing to a black hole was imagined, but because it was too far ahead of its time, it received little attention. Furthermore, given the approximate speed of light at the time, John Michell ran calculations that led him to the conclusion that any star with an escape velocity greater than the speed of light must be 500 times larger than our Sun. Fast forward to when Albert Einstein presented the world with his brilliant theory of relativity. Gravity, according to Einstein's theory of relativity, could bend light but not change its speed. This is because Einstein's theory of relativity stated that gravity is not a force as previously thought, but rather the effect observed when massive celestial bodies warp the fabric of spacetime around them and the curvature causes objects to fall towards them. When light passes through a gravitational field, it is bent due to curvature, but because gravity is not a force, its speed remains constant. So, while Michell was incorrect in determining the mass of stars by measuring the change in the speed of light, he was certainly correct in pointing to celestial things that would trap light due to their vast bulk. Einstein anticipated the existence of celestial planets so enormous that their gravity permits nothing to escape after publishing his theory in 1915. And this was confirmed by Karl Schwarzschild, who utilized Einstein's equations to mathematically verify the existence of such celestial bodies, which we now refer to as black holes. According to the theory and equations, when stars much more massive than our Sun collapse near the end of their lives, their cores become so dense that they bend the fabric of spacetime to the point where the curvature creates such a strong gravitational pull that nothing, not even light, can escape. This sparked interest around the world, but identifying such heavenly bodies proved difficult. After the theoretical existence of what were not yet named black holes was verified, decades elapsed before astronomers spotted a celestial source of X-rays using one of their sounding rockets in 1964. After more investigation and analysis, astronomers decided in 1971 that the X-rays were being emitted by a bright blue star orbiting a black object. They claimed that the X-rays were emitted as a result of the dark object consuming material from the bright blue star, confirming the presence of the first black hole. The designation Cygnus X1 was given to this dark object, which is located in the constellation Cygnus. Prior to this, the term black holes existed, but the terms used were dark stars or collapsed stars. However, John Archibald Wheeler, an American physicist, used the term black hole in 1967 during one of his lectures at the NASA Goddard Institute of Space Studies, and the term was popularized. Many more black holes have been discovered over time, and there are three types of black holes: stellar mass, black holes, and supermassive black holes. Black holes are generated when stars with masses between 5 and 10 times that of our Sun collide. Intermediate black holes are generated when stars 100 to 100,000 times the mass of our Sun collide, followed by supermassive black holes, which are the centers of galaxies. Supermassive black holes have millions to billions of times the mass of our Sun and are the largest black holes known to date. While we know how conventional black holes form, we don't know how supermassive black holes form at galaxy centers. You may be asking how astronomers locate black holes if they are dark and do not emit light. But before we go any further, please subscribe to Zeed by clicking the bell button. Once formed, black holes can expand in size by eating matter. The event horizon is a place near a black hole when gravity is so powerful that nothing, not even light, can escape. Anything that enters the event horizon cannot escape. The radius of the event horizon, on the other hand, is typically smaller. There are celestial bodies that circle black holes but do not enter them. However, under the influence of extreme gravity, matter can accrete around a black hole and undergo the process of accretion, during which the matter spiraling downward compresses and heats up tremendously. Because of the high temperatures, stuff emits X-rays and gamma rays. However, another fascinating event occurs during the accretion process. Magnetic fields exist in the accretion disk and are enhanced when it is bent and crushed during the accretion process. The matter is launched as powerful jets perpendicular to the accretion disk by these intense magnetic fields near the black hole. These jets are so fast and powerful that they approach the speed of light. When astronomers look for black holes, they look for strong X-rays released by the materials in the accretion disk, or they can look for black holes by detecting strong radio emissions emitted by the intense jets of matter blasted from the black hole. Astronomers may also employ alternative techniques, such as monitoring the orbital motions of stars around black holes in order to detect stars orbiting and behaving abnormally about empty space. However, astronomers use a variety of additional methods to search for black holes, including gravitational waves and microlensing. Now that you understand how the existence of black holes was proposed, how they form, what they are, and how astronomers locate them, you may be asking how they breach or defy our rules of physics. So, let's go back to 1974, when an English physicist named Stephen Hawking published his idea on black holes. According to quantum field theory, particles and antiparticles are constantly created and destroyed in space. However, Hawking hypothesized that around the event horizon, things change. Using his theory, he argued that near the event horizon, one particle from the particle-antiparticle pair would fall into the black hole while the other was radiated away. The particle that would be radiated away retains energy, and this radiation was dubbed Hawking radiation, thermal radiation that carries no information. He went on to explain that the production of Hawking radiation from black holes causes the mass and energy of the black hole to diminish and finally evaporate, a process known as Hawking evaporation. However, because Hawking radiation is thought to be very low energy and weak, it has yet to be directly seen. When this hypothesis was given, it contradicted and perhaps broke our physical rules, resulting in a paradox. According to Stephen Hawking's theory, black holes generate thermal Hawking radiation that does not convey information. The emitted radiation is the same whether a star, a book, a planet, or anything else falls into a black hole and contains no information about what was swallowed by the black hole. This suggests that black holes annihilate the information that enters them. On the other hand, it is a physical law that information cannot be destroyed. There is currently no explanation for why, if information cannot be destroyed, black holes appear to destroy information. This sparked the idea in the realm of astronomy that our physical principles break down near the event horizon, and what happens inside a black hole is unlike anything we can foresee. This dilemma and huge contradiction may be answered only if we know what happens to matter once it crosses the event horizon and enters a black hole. Astronomers have never been able to sight inside a black hole since no light can escape it. What confuses matters even more is that the radiation emitted by black holes has no information about the inside. However, astronomers have gone above and beyond to forecast and propose speculations about what might happen within a black hole. According to one hypothesis, a singularity at the point of infinite density and gravity exists inside a black hole. A moment when time and space collide, where our physics simply cannot explain what could or is happening. There have been attempts to replace the concept of singularity with alternative conceptions such as the presence of Planck stars, which would include Planck scale physics. The influence of quantum gravity would be tremendous, and quantum structures may exist with a whole distinct type of spacetime. The firewall hypothesis proposes that there is a very energetic and intense zone near the event horizon that burns any information that enters it. This hypothesis similarly attempts to answer the information dilemma by claiming that information is not lost or destroyed, but rather incinerated by the firewall. Another idea proposes that black holes include wormholes, which are celestial structures that connect different regions of spacetime and serve as spacetime shortcuts. So, it's possible that black holes will move us to a completely different region in space. Another strange notion is that our universe is contained within a black hole, and that black holes may contain new universes. However, this would greatly complicate matters. Consider this: if we, as a universe, are inside a black hole, there must be additional black holes inside this universe, which is inside the original black hole. Then there are other universes inside our universe's black holes, and hence other universes inside the black holes that are in the universes inside our universe's black holes. Can't this just keep going like the Pascal's triangle? With no indication of where to begin or end. Another conundrum under this idea is whether it all began with a black hole or a universe. Is it the egg or the chicken that came first? Isn't it perplexing? However, mathematical calculations indicate that this is exceedingly implausible. But one thing is certain: black holes are exceedingly mysterious and complicated celestial phenomena that science has yet to fully comprehend. And the main reason for this lack of explanation is that they are black. We simply cannot see them. As a result, it will take time for science to evolve to the point where technology capable of viewing inside black holes arise, allowing us to completely comprehend these enigmatic celestial wonders. Give this video a thumbs up if you liked it, and please leave your comments or questions in the section below. And don't forget to click the bell button to stay updated.